So my name is Dąbrowski, and I will be talking here about simulation and trucks. So it's not cars like the usual in this meetup, trucks. The presentation will start with just a brief introduction and a rationale for why to simulate. Many of you probably understand this very well, but I will go over it again, and there is a section about overview of the simulation tools, mostly open source tools. And in these sections, the simulation tooling, I would be very interested about your feedback. So your experiences with simulators, I know probably among you there are some very interesting experiences. And then there will be 2 case studies from the projects that we did in Robocar. One will be concerned with the mine operation, the trucks in the underground environment, and the other is the harbor. And in the end, of course, there will be time for some questions. So that's the team. I'm a graduate of computer science / IT department of University of Warsaw, and I used to work in like 5 years in software engineering in general in various kinds of companies, and then I moved to robotics, and I'm very happy about it. It was like 5 years ago, and I think it was a good career choice. And here is the entire team which was involved in the project. We'll talk about our company is a bit larger, but not too large yet. We are expanding, and more about it on the last slide. So, of course, like the name of the company suggests, you could probably figure it out. We do robotics and also some machine learning. Okay, so why to simulate? Of course, all major players simulate. They have some kind of simulation solution because simulating and crushing a virtual car is much cheaper than crushing a real one, but also for a variety of reasons, like you can generate rare scenarios which are very difficult or dangerous to recreate in reality. For machine learning, you can generate tons of data from simulation. And of course, it's very easy to move to a different location, test different maps, test different sensor layouts. So all in all, it's a must when you're developing solutions for self-driving cars. And of course, here we'll focus on some prototyping of algorithms and also on the scene generation. And our use cases are concerned with real vehicles, so not just simulation, not just for the purpose of testing an algorithm, but as a way in a pipeline, as a point in a pipeline where we in the end deploy the solution and drive on a real track, which is for most self-driving cars or whatever still science fiction. So about the tooling, the simulation tools, you know Carla probably around here. All right, who knows Carla here? Maybe raise your hands. Okay, so not that many people. Just to probe the background, who is a software engineer of some kind among you? All right, that's better. So it's about the profile of the talk, how technical I can get. So you can see 2 screens here. The left one is Carla, the right one is AirSim. Actually, both are Unreal screens because that's the engine, the visualization, the physics engine, the scene engine. So Carla main use case is testing machine learning solutions. So it's for autonomous driving research. It's not the same use case as we have, right? They're important changes. Carla is an interesting project. I think the most interesting. It's still developing. I think the last version was 0.91 or something like that. And it's very promising, of course. We are observing it, and I will be very curious to hear the talk that is later today. So Carla comes with a scene in Unreal, which is a part of a small town. There are some cars, there is a town, there are some scenarios where you can drive the cars around and test for some very basic things right now. AirSim is another open source tool from Microsoft. Air in the name is from the fact that it also serves to simulate UAVs, so drones. So it's a kind of dual purpose there. The scene that they provide with the project is very basic, as you can see on the picture. The advantage is that it builds without any problem. Like I have problems with building Kala. I needed to use my software engineering skills instead of just following the instruction. More simulation tools, open source. There is Gazebo. Who knows Gazebo? All right. So it's an open source robotic foundation tool which has legacy already. It's quite mature. The version is 9 point something right now. The primary use case is from the world of robotics. So robots kind of Roomba-like or humanoid-like. This is a bit different than automotive. So its primary use case is to simulate populations of robots. But also on the screen you can see there's our entire world and a model of a car coming from NVIDIA Challenge, which it's a previous model. It was a challenge for machine learning applications for self-driving cars. Another tool is, Apollo is a project which emerged recently, but is huge because I think it's Chinese mostly, so there's a lot of traffic there. And the purpose is a bit different. This is like an entire framework to deploy on a car. You get a car with a certain set of sensors, and it's ready to go. I didn't test this because it's kind of, you have to buy a car with the sensors, which is quite expensive. It's not a use case, but they also have a simulation tool which is called DreamSpeed. I don't think it's very sophisticated right now. It's a bit of a different use case. So, of course, that's not exhaustive list, but these are in some ways interesting ones. And if you know any other interesting ones that can be applied to automotive, then I would like to know. We can talk, or you can call me now. Anyway, none of this just solves your problem. You have a problem. You want to simulate some kind of scene, a map, a vehicle, some kind of behavior. So you can't just take the tool and you're done. You have to develop a simulation scene. You have to put the correct vehicle model. Of course, there is the entire issue of developing the correct algorithm to drive it. And you want to develop scenarios as well, which are interesting for you. So also taking a tool that is already huge and is not exactly for your use case, it's a bug. It's something you need to support. Sometimes it's better to have something like it. So one tool that is a framework, a middleware, which is very useful in robotics in general, is ROS, the robot operating system. There's a reason why every simulation tool I mentioned has some kind of ROS integration. Gazebo, of course, has a very strong ROS integration because ROS is also from Open Source Robotic Foundation. This is like the same entity. But every other also has some kind of ROS integration. So there are common things you want to do when you're developing a system, such as a system called self-driving and a simulation framework for that, which is you need this entirety of communication, the plumbing, the tools for debug, for monitoring, for starting subroutines, programs. All this kind of so-called plumbing you can see on this bottom picture from the ROS page. This is what it provides. So this is publish, subscribe communication, and which is very convenient for extendable architecture where some entities are dynamic, so they appear, right? So of course it contains many packages which solve various robotics problems like navigation problems, perception problems, so you can just use the code. And the community is great. When you build a project in ROS, you build it in a modular way, which is advised. It's are very supportive of this kind of architecture. And it's becoming increasingly popular in automotive. I don't have stats, but we all get job offers quite a lot. And it's increasingly present in the offers. So there is an entirety of discussion about this, about the industrial readiness of the middleware. But for fast prototyping, there is nothing better, I think. So everybody should use it. So there is also a second version. I advise you to check it out. It's already the third release of this version. So it's ready to be used. And it has also the greatest conference, I think, the community. It's called ROSCON. I very much like it. And on the last conference, like the focus moves towards ROS2. It's very visible. So it's something to consider. Anyway, if you like good colors and turtles, ROS is for you. As you can see, the logos are always, and the names of releases are always some kind of turtle theme. All right, so as I mentioned, there is this task of creating a simulation scene. When you want to solve some kind of problem and simulate it, you want to be able to create a simulation scene in an easy way, have some tool for it. It's like with photo editing, you can use Microsoft Paint for photo editing, but you're much better off using GIMP or Photoshop, right? It's just there are tools for it that make it much easier. And our requirements were to create a network of roads pretty fast, and it's kilometers, like a degree of 5 kilometers. And precision, why precision? Precision with the geolocation, in the geolocation sense. I will explain later why it's important for use case. And also, of course, to have, there is this wish in the entire community of simulation to have something that generates these kind of scenes in an automatic way from the recorded data. NVIDIA had some interesting results with GANs, with generative neural networks. But these are, I think, only visual. We are here mostly using LIDARs. So you can see screens from a tool. We hired a professional company to help us, Vector Zero, and the tool is Roadrunner. So it can, we think it's really good. So we used it also ourselves. And I can see logos of some other software, some of you might know, which are very useful for generating scenes and meshes. So of course, the scene, it's not just the geometry and the textures, it's also logic of the driving, open drive data, so all the kind of meta information about the road. So you can know which side of the road the traffic goes, like which direction. And still the rollers are generated by some kind of simple curves, as shown there. And you can see there is elevation as well. Elevation, if you want to recreate a real place, right? So this is recreating a real place, not creating a fake town, right? Which is based on nothing. If you're recreating a real place, you need elevation data, of course. Unless it's very flat surface. So you can get this from some kind of organizations, government organizations. All right, so let's move to case studies. First case study is in the mine. So we have a track and it's in the mine. It's the limestone mine. First thing you can see, maybe the first thing is the track. But the second thing you can see in these pictures is like there is both open and confined areas. There is plenty of specifics to this, which it's different from the self-driving taxi in the urban environment, right? So we have low light conditions inside the mine. Of course, GNSS, any kind of global navigation satellite system, one vehicle inside this kind of line. So it biases you towards choosing LIDARs. It's around 4 kilometers, and it's intermittent outdoor, indoor, outdoor, indoor. And then the entire problem is to automate transportation of limestone. So there is in one place, there is a bunch of mined limestone, like bricks. They are loaded on the truck, and they are transported to a place where they are crushed, and this crushed thing is taken away, right? So, so human drivers, you know, they just drive the same route all the time, right? They just drive this all day, right? It's kind of boring. It's a very good candidate for automation. The entire, you know, background for these use cases, why this kind of use cases, is that they are simpler. You know, it's a kind of low hanging fruits. So solving a problem of urban driving in a very complicated, unpredictable environment with other human beings, you know, is difficult. This is simpler, so it's expected to hit the market, right, before. So we are solving this kind of use cases. All right. So of course there is this route. The source is actually, this is a public knowledge because this has been released as a PR video from Volvo Group. There is a source on YouTube. You can see the PR video. Everybody is happy about, you know, autonomization. There is good weather in a region where you can't find good weather, I think. So they chose a very specific day for that. But it's fun. It's a good video. We will share the slides later, or you can just follow along. Anyway, there are other trucks also, because it's not just one truck going on this route. That wouldn't be very efficient. All right, so how to solve the problem? We were to start with prototyping. That was, by the way, it's not like we chose this order. It was how we got customer projects, right? They wanted us to do this in the first phase. You know, of course, we are advising our customer in this way. So we started with prototyping. What they wanted us to find, and what we wanted to find, were what kind of deep learning solutions can be interesting based on LIDAR data to find a path in this mine, not to hit walls, basically, right? So the background for this is that there was supposed to be also a primary system that finds the path, and this is a secondary system, much like the concept of arguing machines. You know, there are two systems, each of them proposes a path to go. If they differ, the paths differ, then there is, let's say, dangerous situation. And in the transition phase, the human then takes over, and we find out what's wrong, and we fix the system. So they agree, you know. So we tested this approach, so this is here. There are three. So first is neuroevolution of augmented topologies. So it's an interesting approach to neural networks, which right now Uber is heavily investing in. And how many of you are familiar with neural networks? Like, how much do I need to say? All right. That's good. I like that. No need for introduction there. So in normal neural network, standard neural networks, you have backpropagation as the mechanism to change the network from iteration to iteration. There is no backpropagation in neuroevolution. Instead, there are mutation. The topologies world in this is about network topology, of course. So topology is also evolving, not just weights. So a new layer can be evolved as a mutation, added or removed, and the same in the layer, neuron can be added or removed. And of course, weights also change. So, of course, in this approach, there is something that needs to determine fitness. It's an evolutionary algorithm. So, of course, it's easy. It's similar to reinforcement learning. which has remote function. Not very easy to design in many cases, but the fitness is very much like it. So you can go like for a very simple fitness measure, which is how far you manage to go before crashing. So a distance travel. But of course you need to improve because you want to avoid some kind of wobbly behavior. You know, the track is kind of sniffing each wall. It's not very energy efficient, so we need to develop a little bit better than measure. You know. Anyway, the problem we started solving at prototyping phase is quite easy. It's easy to train a neural network to solve it. We tried different approaches and learned how it goes. But not crashing into a wall on the map like you see on this, in this Gazebo screen on the left side. It's not a hard problem. You don't need high LIDAR resolution. A problem of not crashing into the wall and keeping the distance, it's quite simple for neural networks. So there was reinforcement learning using the advantage active critic. I won't be talking about it here. I will go into detail on imitation learning using convolutional networks. So imitation learning requires human data, right? So of course we had recordings of human drives. These poor truck drivers, who drive through the mine. They recorded some, they got sensors on the truck and they recorded some data from the drives. So we had the correct path to take by the truck. So the one that human took, right? And we have LIDAR frames. So entire table. But of course, to approach it correctly, you need to augment the data because otherwise the system doesn't know how to behave once it's off the path, right? The human driver will always stay on the path, so you don't have this data which is, a bit closer to the wall. So it wouldn't be stable. So we augmented the data in a standard way as well by changing the pose of the truck from recorded frame, like rotating it a little bit, changing position. And then this is on the screen, it's barely visible, I think. Yeah, so augmenting the data is quite easy. You change the position, and you just do this transformation of the frame, of the LIDAR frame. It's of course not perfect. You can't go 5 meters ahead because you would see different things in LIDAR. But small augmentations, like let's say in a range of a meter or two, it's still good. And then it's easy to calculate a curve that comes back to the path as a good thing that a human would do, right? It's an algorithmic thing. So once you have this kind of data, you can train a solution to follow that. So I will have some movies here, starting with Neural Evolution. So it's a simple Gazebo track, but what's interesting is that the track wasn't didn't learn on this particular map. This is a new map. It hasn't seen it before. It's also much longer than the map it trained on. It's a ninth generation from this neat algorithm, which took, I think, 6 or 7 minutes to learn once we got things, well configured and parameterized. And as you can see, it's not like a human driver unless it would be very prime or she, but it doesn't hit the wall, right? It solves the problem. Maybe not optimally, but it does. So, yeah, it's almost the end. It's not sped up, the video. Oh, by the way, that's a monkey on a pillar. That's a monkey on a pillar. The Blender tool has this kind of standard monkey. If anybody, I see some of you nodding. So as a joke, we placed a monkey on a pillar. And also not as a joke, but to test, whether this kind of completely new thing would be, avoided. It happens. So what's interesting, the video is not sped up. We run the simulation with, there's a real-time factor around 4. The maximum we're able to have is like 20. It's also a matter of effective real-time factor because you can run the simulation in parallel. Neural evolution is very good for parallelization because you have The one step is spawning a population of networks, let's say 100, and then you have to wait until all of them terminate to determine the most fit, right? The list from the top to bottom. So you have like 20 most fit reproduce. It's a cruel rule. So the parallelization would be like you can run 10 instances. So 10 individuals in 10 different simulations can run at the same time, no problem, or 50. I think we run 7 because we had laptops, right? To run, not some kind of. So you can run it fast if you get things right. It's a matter of getting physics right in Gazebo 2, and getting physics right when you are speeding up is not that trivial. You have to watch. So next thing is this CNN imitation. There is no simulation. In Gazebo simulation, there is like Python simulation or visualization. So you have two things happening here. You have the original algorithm was trained on the top one, the top map, but going in the opposite direction. So we wanted to test, the other direction, and the bottom one is a new map. So you can see the LIDAR frames, and in the next video it will be also important, so I will talk about it. So this slash on the top is just the max range. It's not detection. Just max range is 1. Like you have to normalize the data from neural networks. So 1 is nothing in the range, basically. But it looks strange. You need to kind of see it. It went through it, right? So it seems that the problem can be solved at least in several ways. Next one is also CNN imitation, but now what is not usual on CNN, we predict like the path. So it's 3 outputs, like it's angles actually. So they create a path, right? 3 points ahead. Because if you want to go at a certain speed, you need some kind of, more prediction. So here we managed to train it on augmented frames from LIDAR data and based on a human drive. So what's next? Next, we are starting simulation now, and here.
What's the output of this neural network?
3 numbers. 3 numbers.
Speed, I guess?
No. There's no speed here. This is not yet the problem to solve. Besides, this is a part of a larger system. So it's a secondary pathfinding solution, which works in a complicated system where it doesn't count the speed. It must predict a correct path, okay? And the speed can be an input, but in this prototype version, it wasn't, right? So we assumed some constraint on the angles, of course. So you can't just turn in place, right? Which would be matching for the speed that is typical, right? So how to automatically create a scene for the simulation? That's an interesting thing. And with LIDAR data, it's easier in a confined environment because you get all the hits, right? So we had this track with LIDARs. 2 of them were 3D LIDARs. One was kind of looking up and around, and the other one was looking forward. So we got this data which is by no means perfect, because when you gather data for building reconstruction, you need to go slowly. The track is driving at normal speed. You don't have that good data then, right? Especially you have a track, the cabin moves. It's another difference with the cars. So if you're using SLAM algorithms, this is a factor to consider. The cabin has some movement. So anyway, joining 2 or more sources of LIDAR data, joining them over time to create a large point cloud. But at the same time, remembering where was the viewpoint, because you need normals. Normals are the little white things that point to the inside or outside of the object. They need to be consistent. If they are not right, algorithms that recreate surfaces, they just fail. So we had this point cloud with normals in top left. Then there was some kind of first attempt with the algorithm. As you can see, it's not every algorithm, not every configuration gets it right. You have holes. It was still promising, right? We went further. This is a Poisson reconstruction with, I think, level 14, so pretty accurate. And what we found out, that transformation we were using to join two different sources of LIDAR data is a bit wrong. So you couldn't see it in a point cloud, because it looks like a point cloud and it's roughly good. But you can see this like, there's something growing on the walls, right? So this is the only problem right now, the imperfection. It's easily fixable by aligning the LIDAR sign with correct transformation, right? We learned that the one that we got from a customer is a bit off. It was okay for them, but for this purpose, with this kind of detail, there is some kind of funny effect, right? So this is quite good, I think. For automatic reconstruction, there is like no manual work. Zero, right? So of course, you need to handle outdoor as well. You need to join kind of pieces that you. It's still some work. This is just we're just starting, right? And we prepared some kind of video for the mining conference, so it's a bit like in a PR. Wait, this is the real video, the real truck driving in the real mine in Norway, right? It's very cool. It's up north. This is one of the LIDARs we use for fusion. As you see, there are ego detections that you need to filter out, so the car sees itself. And then there is a process, let's say, visualized to make it understood for business people as well. And it's increasing level of detail construction. And of course, once you create this kind of mesh, you want some balance between detail level and the size of the thing, right? Then you can simulate the truck. Oh, there's sound. Oh, well, I hope you like engines. It's a Unity simulation, so we had this truck put into it, and as you can see, that's something that was very well received. I was surprised we were able to do that in such time. And of course, this is very like preliminary. This isn't an effort of many hours. It's just it shows what can be done. I think it's a promise. The track is different, of course. Also. You can't load things on this track. That's an asset we have. So of course, there is LIDAR simulation. Here it's like conceptual. This is conceptual view. Of course, you need to develop it. But what's very good for a real use case is that you can see how the LIDAR from the simulation resembles the real one. And you can fix your simulation. So now there's a concept of safety presented, like there's a guy, on the track is going forward and he will stop. It's very unpredictable. I think it stops way too close. If it was a real human, he would run. I would run. But anyway, it shows the concept, right? So moving on, that's what we are doing now with the mine, right? So now we go back in time because this is a separate conceptual thing. So we start from the past here as well. This is a track in a harbor. So the problem is we have route in a harbor it's not a closed road, but there is not much traffic. You are not very concerned about there being a traffic jam, for example. What's important, there are intersections and roundabouts, and you have to obey the rules, of course. But the truck doesn't need to overtake vehicles, doesn't need to do any maneuvers. If there is some guy ahead of us and he's going slower than an autonomous truck, it's already a success, right? So in this case, if we have to wait for someone, it's not that bad, right? So we still need to detect other traffic participants and react to them. If there's someone ahead, if there's someone at the intersection approaching, right, we need to yield. If there's someone on the roundabout, we need to yield. So even though the track stays on the path, it needs to understand what's to adjust the speed accordingly, right? So the problem was completely about the speed control of the track. The track should drive on a trajectory which is predetermined, it won't change, but it should stop, it should slow down, sorry, and it should accelerate back to the speed which is optimal once something disappears. So, it starts with perception. So our first task was to handle perception. And you can see real tracks are in play, right? We researched and chose the ideal solution. They have this setup with 5 layers. ECU is for embedded computing unit. It's something that allows the software to integrate the LIDARs and detect objects. So it's good for detecting other vehicles, right? So we didn't want to implement this kind of things. It's quite complex, right, to do it properly. They did it for like 10 years. I don't know. I'm not sure. Like, it's a big team, 10 years. So it's better to use something that's already there. Anyway, the customer wanted us to have it interface to ROS with the project. They were using ROS. We were happy to use ROS as well. So once we prepared the software, we went with some IPO people and we deployed all the equipment on the track. So you can see a bit of the setup. There are 3 LIDARs in the front. 2 of them on each side are angled. And there are also LIDARs on the steps, which is a very, this is prototype. You don't want your LIDAR to be a bump, right? But it's the first, let's say, the first iteration, right? So also in the target use case, there's a trailer here, but it's a bus to carry it around and turn around with it. And of course, we need the trailer in the end to carry the goods, but right now we are testing it out. In the simulation, we already put the trailer because the simulation is good and it's much cheaper to do so and easy. Anyway, we drove this track with this deployed setup. We added some utility and visualization tools, and we gathered the data. The second phase was actually to do something with the perception. Okay, we know there are objects somewhere of some kind, but now how to behave based on this knowledge, right? So it's a pipeline. It's a rule-based approach. It's not machine learning, right? It's a perception control pipeline. We found that in this case, where we have to only control speed, it's probably better. So what you can see here is some kind of logic for intersections, where you have a car. It's a very preliminary, right? When you have a car in this area and it's going this direction, just yield, right? The area activates, so to say, and it's something you need to stop, right? And here you can see the ERVIS, so our ROS visualization tool, which shows our ego vehicle as a yellow brick because it's a very big representation. There is the white ones are the LIDAR points, and there are red detections with classifications as well. So the detection comes with a classification tag. It's a car, it's a truck, it's a pedestrian, it's a bike. It's sometimes wrong, but there is no false negative in detections, like we have it on. So if there is a vehicle in a distance, it's detected. There are false positives. So sometimes there is no vehicle, but we detect, let's say, something on the right side. Fortunately, false positives are all this kind that they are not in the path ahead of us. they're on the side, right? So you can handle them. Yeah, so to make decisions based on that, we need some kind of logic for intersections, but we also need some logic for collisions and predictions of the movement based on this tracking from the system. And just also building an interface with the whole system. So localization is not up to us. We get the localization from the system. We get the trajectory, and we output the same trajectory, but with a velocity profile. So we have this speed suggestions for the system, right? So after that, let's say, should be a little bit before, but then the understanding of the issue grew